We're going to start this video with a quick review of what it means to factor a quadratic equation or quadratic expression, because we're going to be doing that a lot. If I'm asked to solve the equation x squared minus x minus 6 equals 0, then there are three different ways that I can do that. One is by completing the square, and nobody likes to do that. Another is using the quadratic formula. That will always work, but it's not really going to help us too much in trig. Third way is by factoring. If I factor this, I end up with something that looks like this. X times x is the only way to get x squared here. The 6 can either be 1 times 6. I'm looking at the last term here. So I either have 1 times 6 or 2 times 3. I want these to add up. The 2 and the 3 or the 1 and the 6. I want them to either add or subtract to 1. Okay, 6 and 1 are going to add or subtract to 7 or 5. 2 and 3 are going to add to 5, but if I subtract 2 from 3, I get 1. So it's 2 and 3 that I want here. And then if I were given this and I were asked to FOIL it and get this as a result, then I'd have x squared, and I'd have a 6 back here, but it's negative, so one of these has to be negative. I'd also have a 2x and a 3x, and this 2x and 3x have to add up to negative x. So I'm going to want positive 2 and negative 3 x's. That means this factors like that. Now I can take each of these factors and say either x plus 2 equals 0 or x minus 3 equals 0. We call this the zero product property because if the product of two numbers, a times b equals 0, let me just write that out, a times b equals 0, then either a has to be 0 or b has to be 0, or they could both be 0. So that's the principle I'm using here. Subtracting 2 from both sides of this one gives me x equals negative 2. Adding 3 to both sides of this one gives me x equals 3. And those are the two solutions to this quadratic equation. How does that help us with trigonometry? Well, it doesn't directly, but we need to know that algebra. If I'm given an equation like, for example, sine squared of x plus the sine of x minus 2 equals 0, then I can see that I have a squared term, a non-squared term, and a constant term. Both of these have a variable in them, but they're not just x squared and x, they're sine squared of x and sine of x. So I'm just going to do a little substitution. I'm going to say let t equal the sine of x. Well, if t is equal to the sine of x, then the sine squared of x is just t squared. So that means I can rewrite this as t squared plus t minus 2 equals 0. And now I'm back to just a quadratic equation, which is what I was working with before. This factors. I have to have t times t, and 1 and 2 are the only factors of 2, so I have to have a 1 and a 2. I need a 1t and a 2t when I add them together. First of all, one of them is going to be negative, but which one? When I add this 2t and this 1t, I get a 1t out of it. So I need more positive than negative, right? Because now I have 2t minus 1t. That gives me that positive t. Now, that means that I could set each of these equal to 0. T minus 1 equals 0. T plus 2 equals 0. So t equals 1. T equals negative 2. I'm going to assume you remember all of this from algebra from here down, so you don't necessarily need to write this step. You can go straight from t minus 1 as a factor of a product that equals 0 to just t equals 1. But the thing is, we weren't asked to solve for t here. We were asked to solve for x. X is the variable in my problem. So I have to go back here and replace this t and this t with the sine of x. So I'll rewrite these as the sine of x equals 1 and the sine of x equals negative 2. Now the sine of x equals 1 at pi over 2. So here I'm going to have x equals pi over 2. Easy peasy. This one's a bit of a problem because the sine function, which looks something like this, only goes up to 1 and down to negative 1. It never gets to negative 2. So this is what we call an erroneous answer. There is no solution from that factor. Now I need to go back up to the instructions, which I didn't write here, so let me put those in now. Solve exactly on the interval 0 to 2 pi. By exactly, we mean pi over 2, not some decimal approximation. On the interval 0 to 2 pi means I don't need to write plus 2 pi k here, because I only care about, I'm going to give myself a unit circle because I want one anyway. I only care about the solutions that come from one rotation, right? Now I found that the first solution here is pi over 2, right? So my reference angle is pi over 2. And I need to figure out if there's another solution between 0 and 2 pi to this equation. If there is, it will be a value of x, or an angle value, that has a reference angle of pi over 2. It will also be, let's see, the sine of x equals 1. That's positive, so it has to be in quadrants 1 or 2. Well, the only angle with a reference angle of pi over 2 is pi over 2. If I go all the way to pi, take the sine of pi, put a point here, the coordinates of that point are negative 1, 0. So the sine all the way over here at pi is 0, not 1. The only angle between 0 and pi that has a sine of 1 is pi over 2. So in this case, that's my final answer. But you have to be careful to check that, because that will not always be the case. All right, so that's how you solve an equation of this form. Now you might see a cosine squared here plus a cosine, or you might see a tangent squared plus 3 tangent. So, but you could just make this same substitution. I've used t, you could use a, or you could use y, or you could use theta. You can use anything you want, really. I would suggest not using x, because x already has a value and a meaning here. So if you use the same variable, it just makes a mess. So do pick a different variable, but really, other than the variable in the problem, it can be pretty much anything you like. T just happens to be my go-to. All right, what happens if you have a problem like this, though? This equation is quadratic in form. I have a cosine squared here, but I don't have a cosine squared and then a cosine. I have a cosine squared and then a sine. And so I need to be able to use this technique. I need to be able to put this into a form where both of the terms are either cosines or sines, and one of them may still be squared. To do that, I'm going to use an identity. I'm going to remember that since the sine squared of x plus the cosine squared of x equals 1, I can replace cosine squared of x with 1 minus the sine squared of x. And I'm going to do just that. So I'm going to rewrite this as 6 times, not the cosine squared, but 1 minus the sine squared of t plus 7 times the sine of t minus 8 equals 0. Now, I've used t here because t is the actual variable. I was just writing a formula down over here. I could have written it using t. I could have written it using theta. I just happened to use x. But here it's important that I use t because that's the variable that I'm actually working with. Now I need to do a little bit of algebra. I'm going to distribute my 6. Then I'm going to recognize that the 6 and the 8 are both constants, so I'm going to combine them. That means I'm starting with negative 6, the sine squared of t, plus 7 sine of t. Negative 8 plus 6 is negative 2. And then you certainly can solve a quadratic equation or factor a quadratic equation that's in this form, but I really don't like to work with leading negatives, so I'm going to multiply both sides of this by negative 1. And that just has the effect of changing all the signs on the left-hand side. And 0 is neither positive or negative. So when you multiply it by negative 1, you still get 0. Now, in this case, I'm ready to do my substitution, but in this case, my problem is given with t in it. So I'm going to pick something different. I'm going to say k equals the sine of t. And now I can replace the sine of t with k. and the sine squared of t with k squared. My hope is that this will factor. If it does, it will be because 6 times 2 is 12. 12 can be written as 1 times 12, 2 times 6, 3 times 4, and looks like that's about it. Those are all the products that make up 12, but what I'm looking for is 7. I want two numbers that when you add them together or subtract them from each other give you 7, and it looks like 3 plus 4 is going to work. So I know that those are the values I want. The problem is I have a 6 in the front and this 2 in the back, and I'm not really sure, because of the 6, I'm not really sure what values are going to go where. So I'm going to do another little trick, and I'm showing you this. My assumption is that you know enough algebra that you could figure this out, but I'm going to go ahead and show it to you anyway because not everybody does. I'm going to use the 3 and the 4 to rewrite this problem. So I'm going to start with 6k squared minus 3k minus 4k plus 2 equals 0. So I've used the fact that this 3 and 4 multiply to give me 12, but add to give me 7. But just rather than just factoring, rather than making that my next step, because it's not obvious what those factors would be, I've rewritten the minus 7k as minus 3k minus 4k. Now I'm going to factor these two terms and these two terms. The most I can get out of the first two terms is 3k. What's left is 2k minus 1. I'm also going to factor a minus out of the second two terms because this minus right here. That means this is going to turn negative when I do that factoring. They also have a 2 in common, so I'll do that. And when I divide a negative 2 from 4k, I'm left with 2k. But when I divide a negative 2 from positive 2, I'm left with negative 1. Now it's nice to note that these are the same because they are, in fact, factors of these two terms. They're a common factor of those two terms. So I'm going to factor out that common factor, and that leaves me with 3k minus 2. So now I have either 2k minus 1 equals 0 or 3k minus 2 equals 0. I'm going to need to erase some of this stuff over here. I need more room. So either 2k minus 1 equals 0 or 3k minus 2 equals 0. Adding 1 here gives me 2k equals 1. Dividing by 2 gives me k equals a half. Over here, I'm going to add 2 to both sides. I get 3k equals 2. Dividing by 3 gives me k equals 2/3. Now, it feels like I'm done because I found some solutions, but I wasn't asked to find k, I was asked to find t. So I need to back substitute. I can't believe I erased that. I had let k equal sine of t. So I need to back substitute. I need to rewrite this as the sine of t equals a half, and this one as the sine of t equals 2/3. Now I know that the sine of t equals a half when t equals pi over 6. So there's my first principal solution. I'm asked to find, in this case, all the solutions of the equation. So I'm going to have to say here plus 2 pi k, where k is an integer. And then coming down here, I have pi over 6. So I need a reference angle of pi over 6. And if this is pi over 6, and this is pi over 6, then this is 6 pi over 6 minus 1 pi over 6, or 5 pi over 6. T equals 5 pi over 6 plus 2 pi k. Because this is one solution, and there's another one, and there's another one. Or this is one solution, and there's another one, and there's another one, and so on. So I found one set of solutions, actually two, the pi over 6's and the 5 pi over 6's. And then I have another one here. I have the solution to this equation. Well, there's nowhere on my chart where sine spits out a 2/3. So I'm going to need to use my calculator for this. If the sine of t equals 2/3, then the sine inverse of 2/3 equals t. What is the sine inverse of 2/3? It turns out that it's about 0.7297. I could go, if I went another decimal place, I'd get, it's 729,727, so I'm going to go 72973. 5 decimal places, I like that. So there's a value for t that also solves this original equation, but it's just my reference angle. It's about 70%, a little more than 70% of a radian. So I'm going to have my first radian. Radians are about 1/6 of the circle, so I think it's about, that's my circle, an arc of my circle. Then my radian is going to be about there, and that means that my angle is going to be, my actual solution here is going to be about 70% of that. And I don't really know what that is. I just know it's in quadrant 1 because 1 radian is all within quadrant 1. So 0.7 of a radian must also be in quadrant 1. So whatever this angle is here, it's 0.70, well, we'll just call it 0.73 for now, right? 0.73. That's also a reference angle. I still have a situation here where the sine of an angle is positive. So I have a solution here and I have a solution over in quadrant 3. So my reference angle, 0.73, I'm going to have another one of them over here. That's the same size as this one here. So to find out what that angle is, what I really want is this angle here. I'm going to take pi and subtract 0.73. If I put this, and I'm using my phone right now, so I'm having to use the whole memory thing in my phone. I'm going to clear that, and then I'm going to say pi, where's my pi? Pi minus memory recall equals, and I get 1.3952. So my other angle, the angle in quadrant 2, is t is approximately equal to 1.39521 radians. And then of course I need plus 2 pi k and plus 2 pi k. Now in this case, I can't use the trick of having, of just saying plus pi k, because I have angles of pi over, what did I come up with? Pi over 6, which is here and here, and angles of 0.73, which are here and here. They're all 4 of them are in either quadrants 1 or 2, but none of them line up with the others, right? There's nowhere where one of these angles lines up with an angle in quadrant 3. So I have to list all of these separately in this case. But this is my final solution. Actually, it turns out it's not. I turned off the video and checked my answer because I don't really know. I have kind of a vague intuition of how big a radian is, but I just wanted to make sure. So I double checked that this was the correct answer, and it is. But I was using my phone calculator, and that's a little titchy. It's an old school input kind of calculator, and I wasn't sure whether I should hit enter or equals or not, so I didn't. Anyway, I got this answer, but it's incorrect. It turns out that pi minus this answer here, 0.72973 approximately, is 2.4. So I need to change this. I hope that what I'm modeling for you is reasonable behavior about how to be responsible for your own answers and check them. And, you know, if they're wrong, just fix it. We have 2.411. I'm going to go to 8 places, or 5 places, so 8, 6. And that is my final answer. I would also argue that if you find an error in my work, I am not averse to being, bring it up, mention it, because I am human. I do make mistakes. I think you'll find that most math instructors do at one point or another. I'm not infallible. And I'd rather know that I've made a mistake so that I can fix it than, you don't need to worry about saving my pride. I make mistakes. We all do. So please let me know if you find an error in any of my other videos. All right, so this was a pretty long video. I apologize about that. Let's see, what we're going to do next is The next thing we're going to be looking at is solving trigonometric equations using fundamental identities. Now we've kind of already done that once. I didn't actually, maybe I didn't look ahead far enough. But the fact that this problem had a cosine and a sine in it meant we had to modify it before we could actually solve it. So I'm going to look at this next subsection and see if there's a lot more that needs to be considered. Hopefully it'll just be a fairly short video because we've actually already addressed the situation, at least in one case, in this video here. So I'll see you over in the next video.